Okay, let's move on to question 4, decision diagrams. I presume by now that you have created all the decision trees for all the functions above, using the previous video as a guide to how to go through these. So let's actually look at our decision trees. How big are they? So you can see we have 7 nodes with 3 layers. Now, when you're dealing with only 3 inputs, 8 or 7 nodes isn't that big. But let's say we had 10 inputs. Then we would have 2 to the power of 10 minus 1 inputs, or nodes, which would be 1023. We would have 10 layers, which is fine. And how many terminals would we have? We would have 1024 terminals. That's a lot of terminals. So how fast are they? So going back to how big they were, you can see that the more nodes that are added, these decision trees become quite big. In fact, become very big, and they use a considerable amount of memory. But how fast are they? Well, you can see that it goes X, goes on to Y, goes on to Z, goes on to true. X goes on to Y, goes on to Z, goes on to false. So you process each predicate at most once, so they are linear in time. And everything is only processed once, you're not going through everything twice. So speed is relatively fast, but can they be faster? For instance, if you look here, you're always going to get false. So you have to question, do you even need to go through these predicates? And these are just the decisions you have to think about. How necessary is every predicate? Yes, we just touched on that. So do we actually need Y here? Because as you can see, we're both going to Z's, and all the Z's all go to false. So do we actually need Y and Z here? Because whenever X is false, the result is false. So why do we need these? Same here. Whenever X is true and Y is true, the result is always false. So do we need this Z? So now we come back to the how big is it. So if we actually don't need these predicates, we can actually remove them and just go directly to false, which will dramatically reduce the number of nodes we need. How necessary is every terminal? Now you can see we would have had 1024 terminals using a decision tree. But as you can see, every result is only true or false. False, false. False, 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 false. But you're only going to have true or false. So why do we need a terminal, a specific terminal for every result, when the results are always one of two things? Could you just have one false and one true and redirect all of these into them? So instead of having 1024 terminals, you could just have 2. So basically what we're talking about is, can we make the trees more efficient? And if so, how would we go about this? Now, I've prepared a series of presentations on binary decision diagrams, BDDs. And you can find these at this clickable link. I believe there's 2 videos on BDDs and 1 on the ADD lib. So I want you to go through these videos now And when you have finished them, come back and we will start on question or part D. Okay, now that I trust you've gone through the videos, you now know what a binary decision diagram is and how to construct a binary decision diagram. But first, let's go through this 3-bit example, or decision tree from earlier. And let's apply the rules for creating a binary decision diagram from a decision tree. So you always start off with rule 1. You merge equivalent leaves. So, what does this mean? Basically we mean, here you see a leaf or terminal is false, 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 false. So they're all the exact same. So we can join all of these into one single terminal. Or leaf, if it's the very bottom of a decision tree where the results are called leaves. Because this one remains true and all the rest are false. So we're actually going to do it down here to give it a bit more room. False and true. So now we've gone from our 8 terminals to 2 terminals. And once you do this, you always have to redirect the outputs from the last node into the new leaves. So redirect all the incoming connections. So this went to true, this went to false. Now this goes to false, and this goes to false. This goes to false, and false, and false. So now, we've merged equivalent leaves, we've rejoined all the connections into them, so we've immediately reduced our size from 2 to the power of n terminal nodes to just 2. In our next step, we will merge isomorphic nodes. So 2, merge isomorphic nodes. Now, if you remember from watching the video, this is when the low and high pointers, or false and true, as we were calling them, the dotted line and solid line, both go to the exact same child node from 2 parents with the same variable. So let's say here y and y, 2 variables with the same name. And we have child z, 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 z. So you see this false goes to z, true goes to z, false goes to z, true goes to z. But this is not the same child variable as this child. So it's not exactly the same. What we would mean by this is, let's say we had y, y. Again, this is explained in the video. But if this, let's take this, let's see, this z as an example, and imagine it was here. Let's draw it over on this side. Z. And both, let's say, Z, Z. Now, if this y's low went to here, and low went to here, and this true went here, and this true went here, these are the exact same child nodes that the low and high pointers are going to. These are the same nodes. So this false goes to this node, this false goes to this node. That is not the same as you can see in this decision tree, because this Z node is not the same as this Z node. Yes, Y is false goes here, true goes here, and Y is false goes here, true goes here, but they're on different sides of the tree. So this is when X is false, this is when X is true. So these are different child nodes, so they cannot be joined, so they are not isomorphic. Here they're isomorphic, here they are not isomorphic. So we can actually do part 2 in this example. But there is an example of merging isomorphic nodes in the link here in part C. And often it is required, just not in this example. So let's move on to part 3, eliminate redundant tests. Now, to eliminate redundant tests, all we're trying to do is find where both, let's say, the positive and negative values both go to the same either leaf node or terminal value or node itself. And then that just means this is not needed. So let's take an example. Eliminate redundant tests. So X is false, Y is false. We get to this Z here. Let's take this Z as an example. So when this Z is false, we get a false. When this Z is true, we also get false as a result, as our output. So do we actually need Z? So we can actually say when Y is false, it doesn't matter what Z is going to be, whether it's true or false, we're going to get false. So you can actually remove Z here. This is what we mean by moving redundant tests. You're basically just adding an extra predicate to calculate to actually get the same result. So you don't actually need it. So you can actually just delete Z and redirect. When Y is false, you get false. So let's move to the next value. And this is how you do it. You start with the bottom layer and you reduce. Then you go back up to the next layer, you reduce, and you can keep going up until you get to the can't reduce anymore. So let's take this Z for example. So X is false, and when Y is true, we get to this Z. And when this Z is true, we get false. And when this Z is false, we get false. So no matter what Z value we get, we always get false. So we actually don't need Z here. As we know, whenever Y is true, we're just going to get false. Now let's start with the Z. Let's just start with the Z over this side just to make it cleaner. Again, when X is true, Y is true, we get to this Z here. And when Z is false, we get false. And when Z is true, we get false. So they're both going to the same place, so we don't need it. Bring that back together. So whenever Y is true, we get false. However, now let's look at the Z that's in the middle. So whenever X is true, Y is false, we get to this Z here. Now this says whenever Z is false, we get false. Whenever Z is true, we get true. So we can't reduce this any further because both are necessary. They both get different results. So that cannot be reduced. We need both of these actions, these decisions. So we are done with that Z. You cannot delete it any further, and so we're done with the bottom layer. So let's move up one. You've done the bottom layer, or the third layer. Let's move up to the second layer. So this Y. Can you tell whether we're going to need it or not? So when x is false, we get to y. And whenever y is false, we get false. Whenever y is true, we get false. So again, they're both going to the same place. So we don't actually need y here. So we can actually simplify it down to whenever x is false, the result is false. And if you go back to the truth table that we created earlier, you'll have it in your notes or in your videos, you'll see whenever x was 0, the output was 0. And these are the patterns you have to look for. Now, let's take this y. So whenever x is true, we get the y. Whenever y is true, we get false. Whenever y is false, we get z. Whenever z is false, we get false. Z is true, we get true. So we can't actually reduce this y any further. We get these both go to different nodes. This goes to a leaf, a false terminal, and just goes to z. So that is it. That is our binary decision diagram. And you can see how much smaller it is in comparison to the decision tree. So we previously had 2 to the power 3 minus 1, which is 7 nodes. But we actually only needed 3 nodes. Now, this tree often depends on ordering. So this is also an ordered binary decision diagram. So a binary decision diagram is called a BDD. And when it's ordered like this, it's called an OBDD. Now an OBDD simply means that X, Y, Z. That's for our function. So X always comes first, followed by Y, followed by Z. You can have any order you want. You can actually do Y, Z, X. You can do X, Z, Y, etc., etc. But as long as the order is kept, it's called ordered. This has a dramatic influence on how many nodes you need. So when it's ordered, we only needed 3 nodes. You'll find actually when you change the ordering, you might actually need even more nodes. So actually finding the correct order of your variables is important to reducing the size. And there are certain heuristics that you can use to determine what is the best order, but that is outside our remit. This generally keeps it, so let's say linear in time, as close to linear as possible. When you have them ordered, let's say we needed another node here and another node here. And let's say on the left hand side we had, on the right hand side we had X followed by Y followed by Z, and on the other hand you had Z followed by Y. You would actually find that the amount of node, you would get a node explosion when you do this. This would be an unordered binary decision diagram. So you have X, Y, Z on one side, on the other side X, Z, Y. So in ordered, you got to have the same node on the same layer. So in layer 1 we have X, layer 2 should be all Y, layer 3 should be all Z. This one is not the same, and the size would actually explode to actually get the same output. So ordering is important. What you got to remember is in each layer you should only have one variable type. You have X, Y, Z, Y, Z, X, etc. Now this is also a reduced or BDD. So a reduced, and this is for ordered, for ordered. BDD is binary decision diagram. So this is reduced. This basically means that this BDD cannot get any smaller. So you've applied these three rules correctly, and now you have the smallest representation of this Boolean function. So it is a canonical representation in that no matter who you give this function to, if they apply the algorithm to reduce it to its smallest representation, you will always get this exact representation. So that's what reduced order BDD is. So binary decision diagram, you can, let's say you can just merge the equivalent leaves and not do parts 2 and part 3. That is a BDD. You can do parts 1 and part 2. And again, it is a BDD. And it can be ordered. You can have X, Y, Z. So it can be an OBDD. But that doesn't mean it's necessarily a reduced order binary decision diagram. To do that, you must do steps 1, 2, and 3 to get the smallest possible representation of your Boolean function. Which, as you can see here, which is a canonical representation, which means if you give it to anyone and they apply these three rules to reduce it, you're always going to get this representation. So that's how you know the difference between BDD, OBDD, or BDD. Binary decision diagram is that you can just apply any of these rules to change it from a decision tree to a decision diagram. Doesn't have to be ordered, can be any which way, etc. Ordered binary decision diagram, again you can apply one of these rules, but the ordering is kept. So X is first, Y is second, Z is third, or vice versa, whichever way you want to order them. Reduced order binary decision diagram, you have your ordering is still there, and you've applied all three rules to get the smallest representation possible. That is an ROBDD. And what I want you to do in part D is reduce all the decision trees into, it says binary decision diagrams, but I want you to do ROBDDs. Okay? When people talk about BDDs, they generally mean an ROBDD. That's the standard, whatever it goes to. Everyone tries to make an ROBDD because, well, they're the fastest. Now let's go back to our size and speed and everything. So how big are they? And you can see we've gone from 7 nodes down to 3. So we've saved on memory. How fast are they? Well, now we can see if X is false, we immediately go to false. We don't have to go through Y, and we don't have to go through Z anymore. So they're actually faster in getting to the same result. It's the same here, when X is true and Y is true, we immediately go to false. And it will be the same speed for X to Y to Z, and down to false and true. So the worst case scenario is actually still the same speed of a decision tree. How necessary is every predicate? Well, we need every predicate here to get every result. But as showed in the decision tree, they were very bloated. We didn't actually need a lot of them. And how necessary is every terminal? Well, we only have the 2 terminals that we need, and yes, they are very necessary. But that's all we have. We don't have any bloating. And that is question 4 for binary decision diagram. And I want you to do that for all the decision trees we made for part 2. You'll notice in some that they can't be reduced any further, such as the single nodes. You can't actually reduce X and Y, so they're actually the same as a decision tree. Others will be able to reduce. Some you'll need one Y predicate, others you'll need multiple Y predicates, multiple Z predicates, etc. to actually get the proper BDD structure. But I'm going to leave that to you to figure out what exactly is needed. So simply look at your decision trees, apply these rules, and get down to the smallest representation possible for all your functions. Thank you.